Good morning. Hope everybody had a great weekend. And thank you for sending me your tests. You all did good with sending me that. I have not graded them yet, but I will grade them, and I will text you what your grade is, and I will post it on Homeschool Minder. So I will work on that after class. Right now, I'm going to gather my stuff, but we are going to start Module 13. This is a longer module, so we will spend roughly 2 weeks on this module. You will have a test on Module 13 2 weeks from today. So 2 Mondays from now, you will have a test on Module 13. And we might have time to get through Module 14 before school is out, but only 4 more weeks. So hang in there, y'all are doing good. All right, well, I'll just, hopefully someone will join, but if not, maybe you'll be watching this later. And I'm going to be talking a lot today and doing one example with you, but mainly just discussion today. So just listen and read along. I'm going to start on page 448 today. So this chapter, or this module, is about thermodynamics. Last module, let's see. Okay, so we haven't yet talked about, we briefly, but not much, talked about exothermic and endothermic reactions. So when we did talk about when solutes dissolve exothermically, they're releasing energy or heat. And then when solutes dissolve endothermically, they are absorbing energy from their surroundings, causing the solution to cool down. We briefly talked about that, but we did not talk about chemical change there. That's just a physical change when the solute is dissolving. Sorry, it looks weird. Okay, but this module, we're going to talk about exothermic and endothermic chemical reactions. So as you might expect, chemical changes can also have a release or an absorption of energy or of heat. Almost all chemical changes actually either release or absorb energy. So endothermic and exothermic can also be applied to chemical reactions. So this module, we're going to talk about how that's done. So the first thing that we need to cover is at the bottom of page 448, and it's called enthalpy. Up until this point, we've focused on the substances that are in reactions, but now we're going to talk about the energy change that's happening with those reactions. So endothermic and exothermic again. If a reaction is exothermic, it is releasing energy in the process. So that means we can think of energy as a product in that reaction. So you have your reactants, and then you have your arrow, and then you have your products in your chemical equation. So energy would be a product if it's an exothermic reaction. So opposite is also true. If a reaction is endothermic, then energy is going to be a reactant. So it's going to be on the first side of your chemical equation. This will make more sense when we actually do some examples, but just for now, know that with exothermic, energy is a product. With endothermic, energy is a reactant. Energy is actually never produced in a chemical reaction or consumed, because as we talked about before, energy cannot be created or destroyed, only change forms. So it's not technically true, but it's a good way to look at it. So make sure you understand it's just a convenient way to think about the energy changes that are happening. Not necessarily that we're producing energy or consuming energy as a reactant, but just that we're changing forms. It's just visually in the equation, it helps us out to be able to see that. So energy is not actually being created or destroyed. That's what they want you to know. So where does the energy come from then if it's not being created or destroyed? Well, remember potential energy from last module? So that's what we're dealing with here. So we have potential and kinetic, And the potential energy is the energy we can think of as being stored in chemical bonds in substances. Kinetic energy we can think of as the heat that's being either absorbed or released during a chemical reaction. That's the kinetic energy. The potential energy is in the chemical bonds. And we talked about chemical bonds a long time ago, but we're bringing it back. Remember our Lewis structures? We're going to talk about those again this module, so get ready for that. All right, so let's move on. I'm on page 449. Sorry. Okay, so the substances that are part of a chemical reaction contain potential energy. So every substance that you have in a chemical reaction contains that potential energy, because remember we said every substance in nature has potential energy. An apple, for example. All right. So if a chemical reaction is exothermic, some of the potential energy that's stored in the reactants are converted into kinetic energy. And this makes the reaction hot. Exothermic means releasing heat. So it's making the reaction hot. On the other hand, if a chemical reaction is endothermic, some of the kinetic energy in the surroundings is absorbed and converted into potential energy stored in the products. So one or the other is true. They're both opposites. So either you have potential energy, which is then released as heat, and that's exothermic, or you have kinetic energy that's used, and then as a result, it's stored up as potential energy, and that's endothermic. And that would cause your surroundings to feel cold. So let's see. This is the real explanation for where the energy in a chemical reaction comes from. Potential energy in the chemical bonds of substances involved can be converted into kinetic energy or vice versa. I'm sorry, I don't know why I can't talk today. All right, so we'll still use the convention of that exothermic reactions that have energy as a product, and endothermic reactions have energy as a reactant. So we're going to kind of visualize that now. We're going to talk about an example. So let's pretend, and I'll go ahead and write it out for you. Let's pretend that we have HCl, which you know is an acid, and NaOH, which you know is a base. And then I can't do an arrow, so I'm just going to do an equal sign for you guys, but just know this is actually an arrow here. I'll just do that to help you out. Okay, and we're going to react these together, and you'll get H2O. I apologize that it's not a subscript. And NaCl. Okay, so this is your chemical reaction. Now I'm turning to page 450 if you're following along. All right, so if we were to actually perform this experiment, your reaction vessel would get very hot because this is exothermic. So if it's exothermic, that means energy is a product, like we said before. So we could write it like this. All right, so this is exothermic. Oops, sorry, exothermic, which means it's releasing energy, which means energy is now a product. Remember, if we split our chemical equation here, that this side is reactants and this side is products. Energy is a product in an exothermic chemical equation. Okay, all right, so let's do a new one. I'm going to clear this out. And this is going to be endothermic. I don't know if this is going to let me make it. Okay, we'll try it. Okay, so if we mix, this is going to be a complicated one, H4, here, 2NH4 SCN plus BaOH2 OH2 H2O 8. All right, that is our reactants. You know what? I'm going to erase this. Make it a little bit farther. That's going to produce 2NH4OH BaCN2. Okay. This is your endothermic reaction, which means when you perform this chemical reaction, your vessel is going to get cold because it's absorbing the heat, it's absorbing the energy. Okay, so when we rewrite our equation with the new information we have, we'll put right here plus energy on the reactants side. Sorry, I'm trying to get that really close here. Okay, you get the idea. It is a reactant, not a product, because energy is being absorbed. So you're not going to have energy at the end. You're starting with it. You're using energy to cause the chemical reaction to occur. All right. So that was just some visual examples of chemical equations that would be endothermic and exothermic, so you can see where we're placing the energy with each type of reaction. All right, so let's see. Let's clear this out and talk for another couple minutes. All right, so like we said, every substance in nature contains potential energy. And the energy stored in a substance is called the enthalpy of that substance. Enthalpy. I'm going to write it out for you if you're taking notes. Enthalpy. And that is the energy stored in a substance. Sorry. Okay. Enthalpy, the energy stored in a substance. We're going to use this word a lot, this module, so you want to get familiar with it. And for some reason, chemists like to use the letter H to represent enthalpy. And in a chemical reaction, the substances are consumed and produced. So as a result, there are enthalpy changes. So the energy that's being stored because your substances are being changed, the energy is being transferred. So it's going to be either consumed or absorbed, and that means you're going to have a change in your stored energy. So we're going to use the term change in enthalpy. And normally you would just use a delta, but kind of like last module, I kept saying just change in T because I couldn't do a delta symbol on here. It'll look like this, really. Change in H, and I should use an H, not an E in that one. Let's see. Sorry, that is my best triangle. Okay, change in H. So a change in enthalpy. That's going to be the energy that accompanies chemical reaction. There we go. All right, the energy that accompanies a chemical reaction. Change in enthalpy. And we're going to talk about that a lot, and we're going to do a lot of examples with actual equations. Okay, so sometimes chemists will call it the enthalpy instead of the change in enthalpy, but that's not actually correct. It is the change in enthalpy. So that's what we're going to call it throughout this module. So get familiar with that. it'll look like delta H. Sorry, I felt like I had to sneeze. This is so awkward online whenever you're not in person. It's more awkward to sneeze or drink some water or do anything like that online than it is in person. I miss you guys being here. All right, so like we talked about before, since change in enthalpy is going to be associated with energy, we're going to use an energy unit. So like I was saying, like we talked about last module, we talked about 2 energy units. We talked about, I'm sorry, I keep going back and forth. There's just a couple things if you're taking notes that might help you. So when we're talking about change in enthalpy, we're going to use energy units. And that could include joules or calories. And remember, we talked about last module how 1 calorie is equal to 4.184 joules. So you'll have to know that. And at the top of page 451, it talks about how most chemical reactions involve a lot of energy. So the units that you'll probably see with a change in enthalpy are going to be either kilojoules, which is kJ, sorry, or kilocalories, which is kcal. These are not the only units that you're going to see attached to change in enthalpy, but it'll just depend on the amount of reactants that are consumed. So if we burn 1 kilogram of wood, we're going to have more heat produced than if we burn 1 gram of wood. So that's just going to depend on how much reactants you have in your chemical reaction. All right, so moving on, sometimes you will see occasionally units like this, kilojoules per mole, or, whoops, I'm sorry, mole, or kilocalories per mole. And these units just indicate the energy change when 1 mole of reactant gets consumed in the reaction. I'm just going to move this up a little bit so you can see it. Okay, so you'll see that kilojoules per mole or kilocalories per mole when the energy change is representing 1 mole of reactant getting consumed. So you might see that too, just so you'll be familiar and know what that means. All right, so if, for example, they were to say, they're on page 451, they say 50 kilojoules per mole, simply means that after 1 mole of reactant undergoes the chemical change, there is an energy change of 50 kilojoules. You don't need to, you do need to be able to recognize the units that are attached to the change in enthalpy, but you also need to understand, and I'll type this out for you too, that change in enthalpy can be either positive or negative. So it's going to be positive for endothermic, and it's going to be negative when the reaction is exothermic. And they give you a little table there on page 451, kind of in the middle, and it just shows you everything there. So if the reaction is endothermic, like we said, then your change in enthalpy is going to be positive. Heat is being absorbed, and the potential energy stored in the reaction's products is going to be greater than in the reactants. Okay, if a reaction is exothermic, your change in enthalpy will be negative, heat will be released, and the potential energy stored in the reaction's products is going to be less than in the reactants because it's no longer stored energy, it's actual kinetic energy. All right, so for example, if we're told a reaction has a change in enthalpy of negative 123 kilojoules per mole, We know that the reaction is exothermic because our change in enthalpy was negative, and we can think of the reaction as producing 123 kilojoules of energy for every 1 mole of reactant consumed. All right. On the other hand, if we have a change in enthalpy of 56 kilojoules per mole, then it's going to be endothermic, and we're going to have 56 kilojoules as a reactant. All right, so let's do example 13.1 and kind of see all this in action. Okay, so when CH4, on example 13.1, sorry, on page 451 at the bottom. When CH4 undergoes complete combustion, the change in enthalpy of the reaction is negative 803.1 kilojoules. Write a balanced chemical equation representing this process. Include energy in your equation. Okay, so first thing, you'll notice it says complete combustion, and we haven't talked about that in a while. So we need to remember how to write a complete combustion reaction. Okay, and they told us what substance was undergoing complete combustion. So first, we're going to write our chemical equation. So we're going to have CH4, which is what they give us, plus, and remember in complete combustion, you're adding it to O2, and draw my line. That's going to produce carbon dioxide and water. This is the definition of a complete combustion reaction, okay? So first we have our chemical equation with our substances. Next, we're gonna need to balance the equation. Remember that fun part? Okay, well I have 1 carbon here and 1 carbon here, so I'm gonna hang out there with carbon. Looks like I have 4 hydrogens on this side and 2 hydrogens on this side, so I'm gonna put a 2 right here. And I'll rewrite this neater once it's fixed. Okay, so that gives me 4 hydrogen and 4 hydrogen. But it did also affect my oxygens on this side. So now I have 2 oxygens here and 2 oxygens here. So I have 4 total. Over here, I only have 2. So I'm gonna add a 2 right here. All right, now I have 4 oxygen and 4 oxygen. 1 carbon, 1 carbon, 4 hydrogen, 4 hydrogen. Okay, we are balanced. So let me write that out nicer for you. CH4 plus 2O2, and then that's going to produce CO2 plus 2H2O. Okay, this is our balanced chemical equation. And according to the example, our change in enthalpy was negative. So this means the reaction is exothermic. I'm going to type this out. So change in enthalpy was negative, which means exothermic, which means energy is a product. Our products are on the right side of our chemical equation. So if I were to rewrite this completely, CH4 plus 2O2 is going to produce CO2 plus 2H2O plus 803.1 kilojoules, because that's what they gave me in my equation. Yes, they did give it to me in negative, but that's just telling me that it's a product, not a reactant. It's still going to be positive when I add it on to my equation as a product. Okay, I hope that made sense. If not, we're about to do a few more. All right, let's go to on your own 13.1. Sorry for the noise. Okay, I'm going to clear this out. We are going to do 13.1 together, and then we'll be all done with class for today. Okay, so 13.1, it says to write balanced chemical equations for the following processes, being sure to include energy as either a reactant or product. So I'm just going to kind of write on top a little tip while we're doing these. Let's see. Negative, oh my goodness, I can't type. Negative change in enthalpy is going to be exothermic, which is going to be a product. I mean, energy is going to be a product. If I have a positive change in enthalpy, that means I'm going to have an endothermic reaction, which means energy is going to be a reactant. I'm going to put L for left side of the equation, and here I'll put right, R for right side of the equation. Okay, that's a little tip to help you out. Okay, so letter A says the formation of ammonium nitrate, which has a change in enthalpy of negative 365.1 kilojoules. Okay, formation, that's your keyword there. So we have to come up with the equation ourselves, just like we did in module 6, I think it was. All right, so the formation of ammonium nitrate. Well, if I go back to that table that we've used quite often on page 175, you'll see that ammonium is NH4, and it's got a positive 1 charge. And nitrate is NO3, and it has a negative 1 charge. Let's separate these a little bit. Okay, so if we were to put them together, ammonium nitrate, which is what we're forming, then we're just going to have NH4NO3. That's going to be our product because it's a formation reaction, and formation means we're forming one product. Okay, so I know my product is going to be NH4NO3. And then we know in a formation reaction, you're going to start with all your basic elements, and those are going to be your reactants, the individual elements. So I'm going to have nitrogen, I'm going to have hydrogen, and I'm going to have oxygen, because nitrogen, these are both the same. So just nitrogen, hydrogen, and oxygen are going to be my reactants. So let's go ahead and start writing that out. Okay, so I have nitrogen, which is a diatomic molecule. So N2 plus, I have hydrogen, also a diatomic molecule. And I have oxygen, also a diatomic molecule. So N2 plus H2 plus O2. And that's going to be forming NH4NO3, okay? That's my product. Now, step 2, balance it. So this was step 1, writing my equation. Step 2 is going to be to balance it. All right, let's see what we have here. I have 2 nitrogens here, and I have 2 nitrogens here, so we're good with that. I have 2 hydrogens and 4 hydrogens, so I'm going to add a 2. Now I have 4. Well, I have 2 oxygens here and 3 oxygens here. So I'm going to have to multiply this by 2 and this by 3 because I don't have a common multiple there. So now I have 6 and 6. But this 2 affected nitrogens and hydrogens. Okay, so now I have 4 nitrogens, which means I'm going to have to add a 2 here to make 4 nitrogens on the reactant side. And I also have 8 hydrogens now. So instead of a 2, this needs to be a 4. All right. Let's make sure we did that right. Yeah. Okay, so now I'm going to write out my balanced version. I hope you were able to follow all that. So I have 2 N2 plus 4 H2 plus 3 O2, and that is forming 2 moles of ammonium nitrate, 2 NH4NO3. Okay. Now, finally, I need to add energy to my equation. Well, they told me it was a change in enthalpy of negative 365.1. Okay, so let's look up here. Negative means that it's exothermic, meaning that energy is going to be a product. So it's going to be on the right side of my equation. Okay, so 2N2 plus 4H2 plus 3O2 is forming 2NH4, NO3 plus 365.1 kilojoules. Okay. This is letter A. All right, so I hope that makes sense. We're not keeping this negative. The negative value is simply telling me that it's a product, not a reactant. So we're adding the energy as a product in our equation, and we just add what they told me. So mainly here, you're reviewing your skills of being able to write a chemical equation based on the information that they give you. Okay, let's erase this and go on to letter B. I'm going to erase all this. Oh no, I didn't mean to erase that. Okay, let me erase all this. Okay. Next, we have B, the decomposition of manganese 4 oxide, which has a change in enthalpy of 519.7 kilojoules. All right, decomposition. Number one, I'm writing my chemical equation. All right, decomposition means the opposite of formation. So we start with one reactant and we break it down into its individual elements. Okay, so let's see. It says the decomposition of manganese oxide. So manganese is Mn and oxygen is O. So I need to put these two together. So I'm going to see, they told me that manganese here has a charge of 4. And oxygen, we know, has a charge of -2. Okay, so let's kind of write that down. So we've got 4 and we've got -2. Okay, so remember they told us before, lots of modules back, that if the numbers are not the same, if the charges are not the same, we're going to ignore the positive and negative and switch the numbers, which would leave us with Mn2O4. But this is not the minimum that I can go, because 2 and 4 can be divided by each other. So really, the lowest I can go is MnO2 if I divide each of my subscripts by 2. MnO2. All right, so MnO2 is going to be my reactant because this is a decomposition reaction. So MnO2 is going to form Mn and O, right? So Mn plus O, which is the diatomic molecule, O2. Well, that was easy because now we're balanced. This is already step 2 because we have Mn here, 1 and 1, and then we have 2 oxygens and 2 oxygens. Perfect. All right, so step 3, I'm going to add in the change in enthalpy that they told me. So step 3, let's do that. All right, well, let's go back and see what they said. They said the change in enthalpy was 519.7 kilojoules. That's positive. So a positive change in enthalpy means it's endothermic, meaning the change in enthalpy will be a reactant. So it's going on the left side of my equation this time. So MnO2 plus what they told me, 519.7 kilojoules, forms Mn plus O2. Okay, and we are done with letter B. Pretty easy once you get used to it. Okay, I'm going to erase it and move on to C, and then we'll be done. I'm sure you're tired of listening to me. All right, let's go to letter C. The reaction between H2CO3 and KOH, which releases 21 kilocalories. All right, So step one, we need an equation, right? Step one. So it says my two reactants are H2CO3 plus KOH. Well, you will notice, if you remember, that this is an acid and this is a base. So this is going to be an acid-base reaction. All right, so what we do here, if you recall, I know it's been a long time, that you're going to pull out, you're going to separate your ions, which means I'm going to have here, I'm going to have hydrogen, and I'm going to have CO3, which I believe is carbonate. Let me double check that. CO3, I'm looking at page 175 in case you are too. CO3 is carbonate, I was right. And then here I'm going to have potassium, and I'm going to have OH, which is hydroxide. Okay, so let's look at our charges. So hydrogen, we know, has a +1 charge. CO3 has a -2 charge. Potassium has a +1 charge. And hydroxide has a -1 charge. Okay, so we're going to put our positive over here with our negative over here, and our negative over here with our positive over here. We're going to switch them. Okay, so I do have 2 hydrogens there, but I only have 1 hydroxide here. So I'm going to need 2 hydroxides to accept that, which is going to give me 2 waters. But I'm sorry, I'm jumping ahead of myself. So let me just type it out for you before we balance. So it's going to produce H2O plus, H2O is where my hydrogen joined with my hydroxide, plus potassium carbonate, KCO3. Okay, now let's balance it now. So I had 2 hydrogens. I told you I'm going to need 2 hydroxides, right, to accept those 2 hydrogens. So I'm going to put a 2 right here. Okay, and that's going to produce 2 waters. All right, and then I have potassium and hydroxide. I mean, not hydroxide, carbonate. Well, potassium only has a +1 charge, and this has a 2. So I'm going to need to swap these numbers, right? So that means potassium is going to get the 2 and carbonate is going to get the 1. So carbonate is going to stay the same, but potassium is going to have a 2 subscript. All right, let's see if we are balanced now. We have 2 hydrogens, 4 hydrogens, and here I have 4. I have 1 carbon. Here I have 1 carbon. I have 3 3, 4, 5 oxygen. Here I have 3, 4, 5 oxygen, and 2 potassium, and 2 potassium. All right, we are balanced. So that was step 2. I'll go ahead and type that out for you. I'm hoping this is all coming back to you. I apologize if I'm moving too quickly. If you have questions, feel free to reach out since no one's here today. All right. So I'm just writing this out neater for you, what we just discussed, how we got that balanced chemical equation. Okay, so we had H2CO3 plus 2 KOH, producing 2 H2Os plus K2CO3. Okay, now let's see. Let's look back at our energy. So it says the reaction released 21 kilocalories. All right, well, it's not giving us a positive or negative charge. It's just telling us that it released energy. Well, we know that if a reaction is releasing energy, that means it's exothermic, because if it's absorbing energy, it's endothermic. If it's releasing energy, it's exothermic. So that means I'm going to have the energy as a product. So here I'm just going to add the energy that they told me, which was 21 kilocalories. And that is going to be your final step 3, your chemical equation, including the energy, the change in enthalpy. I hope all that made sense to you. That is all I have for today. And I hope you have a great rest of your day and hope to see you tomorrow. Again, I will go ahead and grade your test, and I'll hopefully send you a text message with your grade and also post it on Homeschool Minder. And I'll see you all tomorrow at 9. Bye.